All right, we're ready to move on. New section, we're going to be talking about what we call geometric sequences. Previously, we've been talking about arithmetic, so arithmetic, the easier ones where your sequences went up by a constant addition or subtraction. Now we're jumping it up and doing geometric, which means the sequences start moving quicker because it's a constant ratio. And a ratio could be a multiplier, a whole number. It could be a fraction, but the numbers are going to change a little more drastically. But let's get started. Looking at today's learning goals, we're going to recognize what a geometric sequence is, find the indicated term of a geometric sequence. So if I want the 55th term, I should be able to find it. And then also find out what geometric means between two numbers really stand for. So let's start with some notes to that effect. All right, geometric sequence, I said, is definitely already a little different because we're looking for that common ratio. And that ratio means we have a multiplier. So think a times a multiplier. It could be a multiplier like 1/2, or it could be another multiplier by 8. It could be a multiply by -2. So these are all good examples of what a ratio would look like. Now, take a look. And let's just make an easy one. If I started with the number 1 and my multiplier was a 3, okay? And I wanted to list some of my numbers. So 1 times 3 was 3. 3 times 3 was 9. 9 times 3 is 27. Even if we want one more, 27 times 3 is 81. We could keep going. Now, it definitely does not look like that arithmetic sequence because in arithmetic, they added to give you the difference. And when I say, how do you go from 1 to 3? Well, that would have been an add 2. But then if I go from 3 to 9, that is not an add 2. So this can't be arithmetic, so we're now looking at a new pattern in our sequence, and it is definitely a common multiplier. 1 times 3 is 3, 3 times 3 is 9, 9 times 3 is 27, etc. So start looking at this and saying, well, there's got to be a shortcut for calculating. And when I have, as you can see, 5 numbers here, so if we sort of talked about their indexes again, and maybe I should try to write these a little smaller so you can see them. There's our first term, second term, third term, fourth term, fifth term, etc. But in between each of those, that is where we're doing our multiplication. So when I had 5 terms, take a look, I only had to do 4 multiplications because you had to have that starting point. So we're going to need that first term as crucial, and then we're also going to need to know that constant ratio. So look at the formula, and you will see those. So by definition, we have T sub n. Any term in the sequence is calculated by taking the first term, timesing it by that constant rate, but notice it's to the power of n minus 1, 1 less than where you're headed. So I was on the 5th term up there, and I would have had my T sub 1 term was a 1, times by my rate or ratio, which was a 3, to the power of n minus 1. If I was looking for that 5th term like I had there, then 5 minus 1 would make that a 4. So I would have had 3 to the 4th times 1 has to be my t to the 5th term. And you can see 3 to the 4th times 1 is definitely that 81. So that's the thinking involved on an explicit geometric formula. And remember, explicit, that's a good word for we go directly to what we're looking for. It's not recursive, and you go one after the other. All right. A geometric sequence is a sequence in which the ratio of successive terms is the same number r, called that common ratio. And I gave you some examples of that up here. And it doesn't have to be a whole number, and it doesn't have to be positive. But there is one number you're probably not going to see. Yeah, some of you are thinking about it. It's going to be a 0. If we had a 0, we'd be wiping everything out. We'd have a sequence that was like all zeros. So, no, we got a slight problem. Now, look at the remaining ones here. The remaining notes say we have a geometric mean. Now, look at that. Read that definition. The terms between any non-consecutive terms of a geometric sequence. So let's just put it in perspective. The terms, those are the individual numbers, between any non-consecutive. We know consecutive means one right after the other. So in my list up top, if I said I was starting with the number 1, and then I went to 9, the term of 3 would be considered an arithmetic mean. If I started with the number 1, and I went all the way to the 81, the 3, the 9, and the 27 would be considered, I said arithmetic, geometric means. Okay? So if I say I have 5 terms, the first one's 1 and the fifth one is 81, you got to know that, oh, that's the second, third, and fourth term are missing. Those 3 terms that are missing are called geometric means. Okay? They're the other terms that are in the sequence, and we're going to work on an example here that shows both how to find terms in a sequence and how to find geometric. So let's do them one at a time here and see what we get. Okay. Find the 7th term of the sequence defined by t sub 1 equals 5 and t sub n equals 2t sub n minus 1. Now, this is probably a little different version of your sequence. So let's write it out and see if you recognize it. What would you tell me if I said, I wrote it this way, a set bracket, and then I said t sub 1 equals 5, and then t sub 2, whoops, not t sub 2, t sub n equals 2 times t sub n minus 1, and then there's usually 4 n greater than or equal to 2. Okay, I don't like that t sub n there. I'm going to clean it up a little. Right here, that should be just an n. This is called a recursive geometric equation. Recursive because you start with the first term, and you're going to get all the other terms in the sequence because t sub n, all right, the phrasing here says t sub n, but then down here it says for n greater than or equal to 2. So that would be a 2 one time, then it'd be a 3, then it'd be a 4, then it'd be a 5. So you'd be finding all the other terms in the sequence. We just have to describe it that way. And then if you think about it, if I have a sequence, and I have the first term, and then I have, let's clean this up a little, and then I have a second term, and then I have a third term, and then we skip some for a while, and I'm out here at the next spot, and then maybe the next one, and the next one. Well, let's say I'm here, and I'll call that the nth term. Then the one that came before it in words is the previous, but how do I write that? If that my notation was n there, this one has to be n minus 1. And again, the one after it would be the next consecutive, and that would be an n plus 1. So if you start looking at what you have, this notation here stands for the word previous term. So you don't want to read it as t sub n minus 1. You want to read it as previous term. So listen carefully as I say this, and this is probably how you want to read or attack strategy-wise in your brain this type of sequence. Find the 7th term of the sequence defined by the first term is 5. All other terms in the sequence can be obtained by taking 2 times the previous term. Oh, and then that makes it a little easier. So here we go. We needed 7 terms. I don't have a ton of room. Let me see if I don't have much there either. So let's clean this up and give ourselves some room to write 7 terms. We're going to write the blanks for all 7 of them. 1, 2, 3, 4, 5, 6, 7. Here we go. According to my thinking, t sub 1, first term is 5. All other terms in my sequence are calculated by taking 2 times the previous term. So I'm on the second term. Well, the previous term is a 5. 2 times 5 is 10. I'm on the third term. Previous term, 10 times 2 is 20. Next term, previous term times 2, 40. Times 2, 80. Times 2, 160. Times 2, 320. Those numbers are growing, and they're growing fast. So it says, find the 7th term of this sequence. We just did. Check it. We got our 320. But by that little definition I gave you and how to read that sequence, that should be of great help to a ton of you in terms of thinking. If n is my term that we were looking for, the one that came before it would be listed as t sub n minus 1. It's better to circle that phrase and think of it as the previous term. Okay? So with that, now let's talk about find the 10th term of the geometric sequence. Now this one's a little different because you're thinking, well, wait a minute, 10 terms, they don't even give me the first term if you look at the information here. So let's undo that, give ourselves a little more room, which we did. Here we go. Find the 10th term of this geometric sequence. They did tell us it's geometric, so we know this is a quick multiplication. So let's write ourselves a little visual to put things in perspective, and it would go something like this. First term, second term, third term, fourth term, fifth term. We'll make a couple others here. All right, now we know first, second, third, fourth, fifth, sixth, seventh, and eighth. Just keep going here. They wanted the 10th. We know we have a second term that's basically 48, and we know we have a fifth term that's 384. All right, so in this situation, you definitely want to reevaluate what you have. You have a sort of a subset list or sequence. So if we have 48 and we really don't know what we're multiplying by, look at the part that you do have. And so in this case, we're looking at the 48 and the 384. And if we have 48 and 384, we know we also have some constant differences. And those constant differences in this geometric sequence is nothing more than the difference between the 2 and the 3 would be one difference, the 3 and the 4, and the 4 and the 5. So if we just sort of subdivide this and rethink of this little subset as a little geometric sequence, we should be able to find our constant difference. Then we can go back and attack and go to the 10th term or whatever other term we want. So here we go. If 48 really is our first term, and so then the third would be our second, and the fourth would be the third, and the fifth would be the fourth. We have 4 terms in our sequence. We have 3 constant differences. So here we go. T sub n equals, this is a generic equation, T sub 1 times, or sorry, plus, no, I was right, the multiplication, and it's the constant difference, and that is, or ratio in this case actually, so I'll say R value to the power of n minus 1. So there's our generic look. Now let's plug in what we know. T sub n in our short list is basically finding T sub 5, but we already have it, so we're going to put 384 there. T sub 1 in our short list is 48. And we know our constant ratio? Not quite. We don't know that. But we do know that it's going to be 4 minus 1 or 3 times. So here we go. And that would give us an R cubed. So with your math skills, you can undo this equation. We have a cube, but we have that 48 there as well. So if we take the 384, clear the 48 from the other side, which would just be a division, we'd be looking at an 8. 8 is equal to that R cubed, so then quickly R, or our constant rate or ratio, is a 2. Now we have plenty of information for us to use. And so from there, we got our 48. If you wanted to complete your list that you have here, you could, times by 2, get 96, times by 2. But really, you want to attack the question that was here, which was find the 10th term. So go back, if anything, because in your equation, you need T sub 1. So if 48 was your second term and your constant ratio was 2, you knew that the first term was a 24. by doing a quick divide, 48 divided by 2. So now we're going to redo this, and we want to do t sub 10, which we don't know. And we do know now our first term is 24, and that constant rate we know is a 2. And now it would be to the power of, we're looking for the 10th term, so 10 minus 1 is 9. So finish the math, and you would do 2 to the power of 9, and then times that answer by 24. And we should be looking at that 10th term in our sequence, and I'm getting a fairly large number. But remember, we're timesing by 2 each time. We're already at our 5th term at 384. So I got a 12,288, and check it. Whoa, we're good. 12,288. Some of you thought, well, that might be a little big, but look how quick these things are going up. And we still had 5 more terms to put on our sequence. All right, so a geometric sequence goes up by a constant ratio. You have another formula to memorize, and that's how you can get any term in that sequence. And obviously, we've already talked about series of an arithmetic, so you know what's coming for geometric. It will be a little different, but let's get this one memorized. We've had a new one almost every time. It'd be a good idea to go back and review them, start making flashcards if you need them, and bring any questions you have about the differences and what the equations really do with you to class.